Okay, so so let us now. So we have done the basically the path factor. So path factor, there is a some sort of a geometric spreading as well as the attenuation. So these two are the path factor contributory things, right? And next is the effect of the site. So that means whenever the recording station is located at a particular place, so that area or that particular spot is on some sort of a sedimentary basin, or might be some soil structure is there, and that will basically amplify the ground motions, right? So this amplification due to the soft sediment present, that we need to take into the account, right, in our recorded data. So how to do that? There are several ways to do that. First of all is the way, if you already established from some other studies the site response, then you can directly use that. Okay, say suppose from some other studies at any place, we have at that particular place we had found out the site response. So what is the site response? So it is the frequency. It is the frequency is plotted here with the site response part. So it is basically the site response of SF, and it will be shown a pictures like these. So that means how at different frequency that site is getting excited, right? So that is what we call it as a site response. Most of the strong motions studies or the network studies of the data, we always calculate these things from the recorded earthquake. So from the recorded earthquake, we always calculate by our routine analysis the site response value of that particular site where the recording is being done. We always calculate, right? So if that data is available, so that means with frequency you know what is the site values, so then you can directly use that, right? Now, if it is not available, so that means there is no such record is present there, then it will be done by means of a study of the underground velocity or underneath velocity structure and the density values. For that, since it's a big project, as I told you, it is a big project, so where a lot of money has to be investigated for the site characterization. So usually if a big structure has to be erected at that point, usually they do the drilling, and from that drilling we always cutting the cores, and from those cores are being analyzed, and we actually calculate the density and the velocity information from that data. Okay, so so that will be establishing the soil type of that area, right? Now, this soil type is a parameter which we, for any earthquake hazard studies, we need to know site specific information. So that means at that particular site, what will be the information? For that, we always need the information what is called as VS30, or somebody call it as a beta S30, because beta is basically the shear wave velocity. So shear wave velocity of the 30-meter soil column. So this is your average VS30 with your 30-meter soil column. So that means the soil column can be much bigger, that's or much depth-wise, but I don't care. I just care the uppermost 30 meter. Say suppose if it is the uppermost 30 meter of the soil column, then what is the average velocity of the shear wave in this soil column? Because this soil column has a different layer. Might be the upper one is a alluvium, next layer might be the shale, third layer might be the sand or something like that, and then we will be from this drilling hole we will calculate that and calculate the what will be the average 30 meter. So that means BS, all the beta values we calculate and then divide by 30. So that is your average VS 30 values. Now this VS 30, average VS 30 is important. If you know that average VS 30 values, then based on that we can use a generic site response values that is available. Okay, so you can, if you know the VS 30, if you have nothing else available, then use that VS 30 to calculate a generic site response values that is available in the literature, and you can use that.
Why we are considering only 30 meter depth, not more than that, 50 meter?
That is a very good question, and that is what we have. We try to understand always that whether instead of a 30, 100 is useful or not, but it is being told that you can use your 100 meter if you are confident on that, but usually the drill data cannot go beyond some 30 meters or 40 meters. So if you can drill up to 100 meters, which is a very difficult thing and very costly affairs, because each drilling is a costly affairs. So if you can drill up to 100 meters, then you have a much more control. But normally people drill up to 30 meter and try to calculate the velocity based on 30, and it has been found that approximation of 30 meter shear wave velocity is a good indicator of the surface amplification, observed surface amplification. So that's why in the design code of the World Design Code or the International Building Design Code, they use VS30 as a parameter to characterize different soil type. So VS30, if it is a more than 1500 feet per second, then we 1500 meter per second, then we call it as a rock site. It is a hard rock site. If it is a less than 1500 to 780 meter per second, 760 meter per second, we call it as a rock site. More than 1500, we call it as a hard rock site, and then it is a simple rock site. Okay, and so there are different category, and then the soil class, site class C, site class D, they are all assigned based on the VS30 measurement. So if you know the VS30, you can categorize all the your soil type. The soil type can be either, the soil type can be A, can be B, can be C, can be B oblique C, can be C, can be D, can be C oblique D, and so on and so forth. They have a different velocity values, and velocity means it's a VS30. So VS30 has been taken out as a parameter for earthquake hazard assessment, and this VS30 is included in the seismic design code. So therefore people are using or try to use the VS30 mostly. Okay. So this is what is called as a NEHARP classification. It is called National Earthquake Hazard Reduction Program of United States. So they have these characteristics, and these are basically followed now by everybody. Every country has this type of these things has been accepted because International Building Code, they use that directly, that formula. So that's okay. So that's the part. So what is the amplification? It is the source beta S over rho S. So that means source impedance, because rho into beta is basically called the impedance. So this is the impedance at the source, and this is your rho bar and beta bar. So that is your average from the source to the site. What is your average rho and average beta that we need to calculate? So this is your frequency dependent as it goes to the deeper. So then this is your GS is the rho S base, and G bar F equals to rho bar F and G bar F. So that you can calculate. So so this G bar F, it can be calculated as the density variation with Z, and this is the beta variation with G over a time, and then we are trying to calculate, this is your 0t dt, and that will be the mainly the rho F will be equals to this one, and 1 by beta F will be equals to this one. If you do the mathematical things, I think your friend needs to be good mathematician, so he can do that. But for me, whatever I got it, that's fine. So we are trying to calculate the average. So then from the source, there is a rho S beta S impedance, and whenever it is passes through and reach the ground, so then each one I have calculated the impedance values and that ratio, and take the square root, that will be the amplification, right? So so that's your amplification of the ground. But also the attenuation, or there is a part, it's called a DF, right? Now DF is basically, you can see it here, that this is your AF into DF. Now this DF, so this amplification is here, and then this is what we call it as a diminution effect. So as you have seen that our spectral structure is basically rising this, and after that it's decayed, right? So that means it goes attenuation, and this is what we call it as a diminution effect, right? So this is your diminution, or we can call it as a high cut filter, right? So that means high frequency we are getting cut. So that is your high frequency cut. So this is your high cut filter. So we have to introduce a high cut filter to our data so that it will be proper, this type of shape. Otherwise this will be a amplification like this, and it will be go on, but it will not go on, it has to come back. Okay, so that is your attenuation effect. So that is your diminution effect. Now these diminution effect can be done in two ways. One part is this, that we have to provide this frequency. This frequency we call it as a F max. Okay, so we have to give this frequency. After this frequency, the things will be given down by the values of F, right? So these things is given by dF is given by square root of 1 plus F by F max. You give the F max. F is all the frequency I am trying to calculate. Okay, so these are the frequency values, and 1 by F max with the dF to the power 8. So that is our diminution effect. So that means it will rise, then stay, and then F max will be coming down. Now what is your F max? Now there is a big controversy between the two schools of thought. One school of thought is Papageorgiou and Aki. They decide that they told that this F max is coming from the source, right? So F max is coming from the source. So it is a source related property. But there are another group of scientists, it is called Hanks. They suggested that it is basically the effect of the site. So whether it is a site or it is a source, that's a different contribution or the different thought that scientists can fight among themselves. But the fact is that the observed spectra says that it decays after some frequency. The things are decayed, and so that values we need to understand. Now, if it is a source part, what will happen that that in a source there is a rupture took place, right? Now this rupture is ruptured, and then there is a barrier, right, which makes the rupture stop. Okay, might be some other portion get ruptured again with that thing, but some things getting stopped. So this barrier, actually Papageorgiou and Aki has said that this barrier is actually provide you the information of your F max. So, but that's okay. But I personally believe that this has a both site and source effect is present there. It is not only always the site, and it is not only always the source. So both are present. So F max value in any area, it goes from 8 Hz to around 12 or 15 Hz. So if you can use a value of this number at this point 8 to 15 Hz, then after that the things will be going down. So this is one of the observations. Basically you are introducing in the system a high cut filter. So that means it has to be cut and it has to go down. Okay, so so that's a high cut filter, F max to the power 8. Another group of scientists, they said that no, this can be done by using another type of filter. It is called kappa filter. This is the Greek word kappa, so it is called kappa filter. This can also be used to model that part. So if you, instead of these things, if you use it as a d pi k0 into f, that also can basically go down the observed response, right? So that we can also use, right? Now, as we have seen that if it is a rock site, then it will be a more or less it will be the kappa 0 moves like this. But if it is a soil, they have a different number. So that we can calculate from the recorded data. So kappa is a factor which we can use. Now, if you can go back to our very first equation, you can see that we have a source path, we have a site path, source path, path, site path, and then there is an instrumental effect, right? IF is the instrumental effect. Now this IF is given as a 2 pi I into F, right? So this to the power n, right? If it is if you have an acceleration record, which we in general we have, if it is a strong motion, we need to have a n. So then then have acceleration, then n value in that case will be equals to 2, right? If it is an acceleration record, n equals to 2 if it is an acceleration record. If n equals to 1, then it's a velocity record, right? If n equals to 0, then it's a displacement record, right? So basically what will happen is this, that IF will be equals to, we all multiplied with a 2 pi f whole square in front, then we have a c into m0 into path part and the site path. This will be all this way, right? So that this will be, this is our observed record for any m0 and r. This will be equals to 2 pi f square and all these things, right? So if it is an acceleration record, there will be a 2 pi f square will be multiplied. Make sense? If it is not a acceleration record, if it is a displacement record, then we will be cutting this one 2 pi f, right? So if it is a 2 pi f, then it's a displacement record, right? Then it's a 2 pi f, it is a displacement record, right? If it is a nothing, just only cm0 this one, then it is basically the displacement part, right? So if you are trying to calculate the response spectra things, then you make the IF will be equals to Vf square into this one. So this is your instrument. If you try to calculate response spectra values, but we are not doing it at this stage, so we can keep it as such. Now, so what it will be given you. So
how the instrument response is changing the response spectra. Like it is the 2 pi f to the power n.
600
So actually it is
right?
this.
So
To that relation, that I'm telling
these
this
are
all these
all images.
instrument response is changing the response spectra. And the
So if I try
no,
to
the response
calculate
spectra,
this,
no, it's an amplitude spectra.
this is
It's a
value.
Fourier spectra.
So average
The response
is
spectra part,
30
if you
will
have
be
to use
equals to
that, you have to use
this
this
will
one.
be the 30 meter. That's sure. So the
That you have to use this one.
upper one
It
will
is
be
a-
the 30 meters.
It is a
but amplitude spectra is either with a 2 pi f square and all these things, right? So, and I have already told you in your Fourier spectra calculation that if you integrate the acceleration to a velocity, then basically in the time domain, if you can do if we have the acceleration, you get the velocity function as a t, when it will be equals to our integration of this acceleration, or a will be equals to dv dt, right? So that means integration of a dt is actually gives you v, right? So the velocity. So this is your integration in a time domain, right? So this is your integration, and you can get a velocity. If you integrate your acceleration, you will get the velocity, right? So that is what you are doing in the last evening, right? So that's your integration to the velocity. But if you need to convert the acceleration, take the acceleration spectra and then try to calculate the velocity spectra, then you have to take the acceleration spectra, and so you have to do, what you have to do, you have to divide by with a 2 pi f, because acceleration spectra with a 2 pi f square, and that will be with all this number. So that means your velocity spectra, it can be done that divide the acceleration spectra, whatever is the acceleration spectra you got, you divide it with a 2 pi f, then that will be your velocity spectra. Right? So, so if you have a acceleration spectra, just divide it with a 2 pi f, all the values, all the frequencies, then you will be getting a velocity spectra. If you have the velocity spectra, divide it with another 2 pi f, you will be getting the displacement spectra, and so on and so forth, right? So that is the in a frequency domain, it is very easy operation. So just only divide it. So have this thing, divide with the 2 pi f, and that's it. That will be giving you the velocity spectra, not the velocity spectra. And then you can take the Fourier transform of that velocity spectra, you can get the velocity in time, right? So that's a inverse Fourier transform, you can go to the time domain. So that is possible, right? So now this entire exercise, so that means multiply CEM0 with a SA, SB, with your path part, with your this one, for a given magnitude and given distance, we will be getting a shape like this. We will be getting a shape like this, nothing else. We will be having a shape like this. So this shape, we can find it out with some amplitude, maximum amplitude. So that is what we can get it from this magnitude and this one. So this is the shape, nothing else. We can get the shape. But the shape is not giving you the time history, because I need the time history. So what I have to do, I have to multiply it with some, so I have to get a pictures like this. So that means this will be some functions like this, right? So then only I can take the inverse, the Fourier transform, inverse Fourier transform of this one, and that will give me the time series, right? So this shape will not give me any time series, because the shape is the only thing. So I have to multiply it with something so that it looks like this shape is like this, and this will be looks like this, then only you can get the time series for here. If from the frequency domain, you can convert it into the time domain, that you have to do it like this way, right? So for that, we need to generate time series, right? Now, how to generate now time series? Because I know that if it is a M magnitude earthquake or MW magnitude earthquake, its amplitude will be like this, and the shape pattern will be like this. Now, what I need to do is to generate some white noise. I generate a random noise, and that random noise, I take the Fourier transform of the random noise, right? And then multiplied it with this shape factor, and then calculate the data with the noise, and then take the Fourier transform. Let me first tell you the pictures, and then I will be coming back here. So, so what has happened, that I generate a white noise. So this is the totally noise, just random noise, make it a time series, make it a random noise, okay? So this will be just only a noise values, right? Nothing else. Now this noise, I need to look like a earthquake. I need, because this is not an earthquake, so I need to look it like an earthquake. So what I do, I will be multiply this noise with a window shape functions like this, and so that will be a pictures like this now. So this now looks like an earthquake, right? So it will be start here and then gradually it finishes, right? So this is your window shaping. So that will be coming out, how to do this windowing of this random noise. So I multiply the random noise in time domain. So this is your time domain function. I multiplied with a window. And if it is a window, then it will take a shape like this, and that shape looks like an earthquake, right? And then we make this shape, and then we take the Fourier transform of this one. Okay, I take the Fourier transform of this shaped noise, I take the Fourier transform. So then this Fourier transform will be like this, okay? So because it's a noise, so there will be some Fourier transform of it, so that's fine. So that I got. And then I make these things, I already got it, I just make it a normalized, right? I make it a normalized. Now what do you mean by normalized? So that I make the maximum value 1, right? So 1 of the maximum value, it becomes the 1. So that is what I have on a normalizing. So that means this is your window values, window spectra. I take the maximum value and divide it window spectra with that value, so that maximum value becomes 1, and that's it. So that is what I have done with a normalized it. Now after I do the normalization, next I multiplied with this shape whatever I have already generated. So these things I have multiplied with that shape whatever I have generated with your source site and this part. I multiply this one with this shape, and then it will looks like a pictures like this. So this is after these things we multiplied with, just multiply with the shape factors, with the shape whatever I have done. So then becomes this one. So now this has raised, because it was now only one magnitude, one amplitude. Since I multiplied with a spectra of the magnitude of the earthquake taken into the account, so then it will be raised to something around 100 or 200. So that will be raised, that number, and then this will be a spectral shape, and that shape is conformable with the earthquake type. And then I take the inverse Fourier transform of it, and that becomes the generated earthquake. Make sense? So that becomes the generated earthquake of that magnitude. Now this is only once, right?
But the generated earthquake depends upon your random noise. Means how you will select that random noise, means up to what frequency. Whether depending on frequency of the noise.
I have generated all the frequencies possible, because the random noise is a random noise. So that does not need to be any values. So just only amplitude values, and that amplitude, whatever it has been generated, that will be converted to a frequencies part by taking the Fourier transform of this one. So then
So I think maybe what to try to say is that because of writing the white noise isn't going to impact the real values of the earthquake.
SM1
Because we are multiplying it with the
we have generated earlier, and this shape has an amplitude which is based on the magnitude of the earthquake, whatever we try to do. So these things has to be multiplied with whatever the noise Fourier spectra is there. So this is also Fourier spectra, but it is a shape multiplied with a noise Fourier spectra, and multiply with that things will be given you the amplitude of the generated earthquake with that much of magnitude, because this magnitude is only 1. So I can multiply it with a 10 with the proper shape, then it will be looks like this, and then I can take the inverse Fourier transform that will contains all the data. right? So that's our target. Now, question is this. How do you take the random noise? Now, one random noise, if you take in the next another random noise, since it's a random, the time series will be different, right? Because it's a random thing, so the time series will be different. Now, what we do is basically for each one, we calculate the peak values and all these things and try to generate 100 or 200 type of random noise generations, okay, and try to take an average value. So then we can say that this magnitude of earthquake at this site will be in this range. So the peak ground acceleration, peak ground velocity, the response spectra, all these things will be in this range. And if you have that much of mean values and a proper standard deviation, then I think the engineer can use that thing as the much more reliably than if you do not have anything else, right? So, so instead of not having anything else, then at least with this magnitude, with this range, and with this shape, I can generate a comparable type of earthquake and try to take a lot of realization, and then we can generate a shoot of time series, and from this shoot of time series, you can calculate the average values either in a PGA or in a PGV or in a response spectra, and you can compute the mean values and standard deviation so that you have a fairly good idea that this magnitude of earthquake at this much of distance can do it like this way, right? So this you can see it, it's a zero noise, zero mean, and if you can see that they have a 1 is basically the standard deviation is the 1, right? So that way it can generate. So this is just a generation of white noise. So there are steps. Now the steps is this. First is the generation of white noise. So this is your normally distributed white noise. Okay, so this will be normally distributed white noise, and it will contain all frequencies are present, and this is we used for the generation of this. And then we need to, when doing the white noise, as I said, we need to multiply with a window. So this white noise will be multiplied with a window function. I will come to that. And then after doing the window function, it will have a shape like this, which looks like an earthquake. And then it will be, we take the Fourier transform of it, make it a frequency spectrum. And so the frequency spectrum will give you the frequency content of this white noise. And then it will be, we make it a normalized this frequency spectrum from here to here, just make the amplitude values is 1, maximum amplitude is 1. That is what we try to do in the fourth part. Then multiplied it with your the modeled ground motion or the shape, whatever we have generated based on the magnitude and the distance. So that we multiplied it. So then if you multiplied it, it will be like this one. Okay, so it will be looks like this. And then you take the inverse Fourier transform to go back to the time domain. Okay, and then after you get the time domain, you can take that response spectra calculation of that time series. You can get your PSV, SA, PSA, and you make lot of time series because it's a computer. Just give whatever workload you can give, they will never say no. So you can go on calculating as many as possible and that things. Now, so the next thing is left is is a window shape. So that means the shaping function. So that means how to make the noise to looks like an earthquake type, right? So that's a window function. Somebody earlier tried a box window. So just a box, take the box out. Okay, so that window function will be a box. But that does not make any proper shape of a earthquake type. So then there is a person in 1974, they had completely defined in a different way, not for this earthquake part, but they have a idea to window it like this way. Okay, so that type of window function, it is called W. So this window function is given as a 3 parameters. We need to give A, B, and then C. So these are the 3 parameters we have to give, and the mathematical shape of this one is basically A T by Tn and exp of C by T by T eta, right? So that's the function. So that you have to provide with the A, B, C are the 3 constant values. Okay, so A value is basically epsilon log of eta, and this one, C value is B by this, A value is this by this. So that's the 3 numbers. Okay. Now, so you can see from this picture what is called epsilon. So epsilon is basically the time in this domain, so how far it will go. So that is your maximum peak, right? And then this will be equals to your eta values, and this is your t eta, and this is the function t, right? Now this t eta part, okay, the t eta part we need to understand, right? So because if it is a big earthquake, then it will have a duration, right? It will have a duration. If it is a very small earthquake, then the earthquake will be like this. The duration will be small. But if it is a large earthquake, it will be for a longer durations, right? So that duration will be given by this t eta part. So that will makes this one. So from the point wherever you cut it, it will be a proper duration. So that means if it is a large earthquake, then you cut it like this way. So it will be a big long durations, right? So this t eta is basically equals to ftgm. So it's the ground motion, and this is tgm. So tgm is the duration of the ground motion, and we select this tgm equals to 2.0. Okay, ftgm equals to 2.0, and this tgm is equals to is basically related with the source as well as the path, right? So if it is a source, it will be generating the earthquake, then that is also big magnitude earthquake, means its duration is more because it will be radiating for a long time. So that will lengthen the time series. So basically that's a T source, and this one, so that so ftgm is equals to 2, and this tgm equals to T source plus T path. Now so T source is equals to, so tgm, so T source is equals to 1 by fc. Fc is the corner frequency, because I told you that the corner frequency is actually depends on the how the earthquake get ruptured. So that means this is the part. So that means it is here, it's ruptures, and then this is your, whatever we call it as a rise time, right? So that is your rise time. If it is a big earthquake, the rise time will be a little bit big because it will rise for a long time. If it is a small earthquake, then the rise time is very small, right? So this rise time, so this is your TR, or the T rise time. So your frequency will be, so this your T time will be equals to 1 by of your FC. So based on your corner frequency of your data, this FC is basically related to the your rise time of an earthquake. So this is 1 by, so that means more bigger is the rise, so that means frequency will be shifted towards the low frequency side, right? So, and that's the part, because that is what I told you, that the spectral shape is like this. So that means if you have a big magnitude earthquake, the corner frequency will be the lower value, and if it is a small magnitude earthquake, the corner frequency will be a little bit high values, right? So this corner frequency 1 by FC will be equals to this, or somebody likes to take it as a 0.5 by FC also, half FC. So both are possible. So somebody take 0.2 FC and this one. But the T path will be equals to 0.05 multiplied by R. This is your empirical relation that they got it, and that value will be giving you better results. So basically your TGM will be equals to 1 by FC plus 0.05 into R, and then it will be equals to your multiplied by 2, that will be equals to T eta. That T eta, you can use that to calculate that what will be these values, right? So that you can formulate to compute these numbers. Okay, so then you can generate this one. So what you have to, if you write a code, then whatever the things you need to do is to just give the two parameter. One is the distance and other is the MW. And then sit together, computer will calculate and give you the time series. You take the either the PGA, PGV, since you now want to know that how to calculate, so you can do the PGA, PGV, and also the response spectra. If you have seen the yesterday code, then you can calculate the response spectra, spectral acceleration of the earthquake, and then it will be fine. So if you can generate this one, then you have a basis to make the structure to be tested, because the engineer always build up the model and then they try to give the input motion to the base and try to see how the building or how the building vibrates based on that input motion. So that is basically what we need to compute. Okay, so if you can give that to the engineers will be happy, and then your job as a engineering seismologist is getting a full credit. Okay, so that's the part. So in order to do that, there are a lot of other things you need to understand. First of all, you need to make it a drill, get the soil information and calculate correctly the VS30 values, right? So that is the first thing required. The second thing is required is this, to see the catalog of an earthquake in that area and try to see which earthquake has a contributory factor in that particular area. So you need not to generate suppose I have seen that there is a 5 magnitude earthquake with a 70-kilometer source zone, that is a contributory factor. Next, there is a suppose 50-kilometer source zone, there is a 9.0 magnitude earthquake is there, right? So that way different source zone. So see, suppose if earthquake has if this is a place, if this is a site, there might be one fault like this, fault number 1. There might be a fault like this, fault number 2, fault number 2, okay? There might be another fault, it is a fault number 3, fault number 3. And each one is contributing to the earthquake at this site, right? So everybody is contributing some earthquake. Now this fault is capable of magnitude 5.0 magnitude earthquake. Let's see, this is on 70 kilometers. This fault is capable of 8.2 magnitude earthquake, is basically 50 kilometer distance. This might be 4.5 magnitude earthquake, and this might be suppose a 100 kilometer distance, right? So this is the place where I like to do. So what should I concern with? Should I concern with a 4.5 at a 100 kilometer distance? No, because the builders know how to address a small magnitude earthquake, because their design work is more or less that type of things they can handle off. So they don't need your advice. Okay, so they know how to construct. But if it is a 50 kilometer distance and 8.2 magnitude earthquake, then definitely it is an interesting thing for the builders. And builder needs to know how much and what this structure will be constructed, so that the building will not set into the resonance with this magnitude of earthquake, right? So so then they need to. So we do not then need to do all this 5.070 and this part. We will be doing only analysis for this one, okay? Now, if you have a record at that point with a previous record of something around 8.2, the engineers will not ask your help, because engineer knows that there is a record, they can, and that's a actually recorded motion, so they will be pleased to use that record, or might be the similar size record. So this is the way they will perform. But if they don't have a record in that area, but they know that that fault can generate 8.2 magnitude previous earthquake, when there is a possibility, the geologist will say that, hey, this fault has a capability of 8.5 magnitude earthquake in another 100 years, or might be another 200 years, then the engineers need to exercise this one. But since there is no record at that time available, so then they will be asking you, the engineer seismologist, to generate realistically a ground motion which they can use it to test their structure things. So then they will give that things, and based on that knowledge, they will be design the structure. Okay, but definitely at that site they need to do all the borehole information, or the seismic cone penetration test, or all these things. So try to get the seismic velocity, density calculations. They have to do that. Okay, if you are building a big structure, you have to spend the money for this one. If you have a 2 to 3 story structure, engineer says, okay, I can do these things without any issue. So that will be fine. But if it is a 12-storied or 15-storied structure and very important structure, then they need to do these things. Okay, so any other question? So these things we need to generate. Okay, now the task will be to generate this time series from the two values on the magnitude and the moment, and use this shape factor formula to calculate this, and then windowing function to get these numbers and multiplied it. Now this, whenever you multiplied it, you have to multiply both the upper side and the lower side, so that it will be, so this function I have defined it like this. So we also need to have a minus sign or the negative side, so that it will be both the upper and the lower value. So it will be multiplied with both an upper lower, and then it will be looks like this shape. Make sense? So this is a WT has to be W minus, WT has to be the reverse 2, right? So then it will be taken care of the entire part. Okay, and we can compute the Fourier transform based on this. Now, so this is first of all, it's assuming a point source. So that means we are assuming this earthquake is being generated at this point, at a particular point here, at some distance from here, right? So this distance, we assumed it as a straight line, and this earthquake is this part. Now, if we have a extended fault, so then we make the fault in some grid like this one, and then this is your recording site, right? So we start the rupture from this point. So we calculate the time distance. So this distance will be the distance, and we calculate this one. Then we loop it over. We have given the rupture to some sort of a velocity. So this is your rupture velocity, which you can decide, and then it will be reaches at this point after 1 second. So then we can calculate it again, these same things, and then when it will be reaches here. So all will be delayed by a time, and then you summed over all the times at this point. So that will be your finite fault model. So that can be also done. So if it is a not a point source, if it is an extended source, or the finite model with your length of the fault is L and the width of the fault is W, then we can also calculate this point source model, but only we have a delayed response. So that means this response first calculated, plus after some time this response will come, and we will be calculating from this distance. Then it will be coming from there. We have to add it at this distance, and that will be continue, and then we will be summed over all the things. That will be the full waveform for the stochastically generated thing. So stochastic generation, as Dr. Agarwal asked, it's basically, it does not contribute any path or any in between, whatever is reflected or refracted, we do not need to know. Also, we are only generating via the random noise. So this is nothing, is basically the actual things, only the random noise are being generated, and that has been set in a proper window functions, and then we multiplied it, and so that is here. It is your stochastic, and it will not be real in that sense, but it will be, if you do it in a number of times, lot of realization, then you can get a ensemble average of all the things. Does it make sense or no? The rupture has taken place at a particular point, and then it propagates, right? As soon as it's propagated, before it get hit by a barrier, it will go on, right? So then that rupture will be basically affecting the record, right? Because as the rupture progresses, but every time that each and every point will be getting transmitted to the record, So we'll have a one rupture comes, so then that will generate this record, right? So then the next point, the next second there is another rupture came, it will be like this. Next time there is another rupture comes, it will be like this. So therefore we have to now add all these things together to get a total response of this earthquake. And then there is a barrier, so it stops. Then it will be again some other part get ruptured. So sometimes in our recorded earthquake, we have the clear indication of 3 ruptures. So that means rupture comes, then it stops somewhere, and then again some other part gets ruptured, and then that will be propagated. So the entire earthquake, if you can see the recorded time history, it will have a 3 different or 2 different type of fault ruptures. So that can be mapped. Okay.